Okay, I'm going to attempt to do an anatomy nervous system notes. Yeah, I didn't get too much sleep last night. Hope you guys got more than me. And I just want to say I miss you guys and hope to maybe Zoom or something. So that would be more fun than this. I got to do this just weird overhead camera thing. It's not too bad. Let's zoom through it and you can give me questions later. You should see my setup though. It's pretty hanky. So what we're going to do is nervous system, and today we're going to do also the reflex arc, which is nervous system response, and what a basic neuron is, the peripheral nervous system versus the central nervous system, and the synapse, how nerves talk to each other. Yeah, so what the heck is a nerve or a nervous system? The signals being transmitted, we've kind of just studied a little bit about that. Nervous system really are, let's say, nerves and special cells. That was a weird N. I'm using a pencil. You should be proud, so I can erase. That transmit signals. All right, that would be like the, in a nutshell, definition. Perhaps getting deeper, you could say that it collects and processes sensory input. And responds appropriately, if at all, hopefully appropriately. Those are my weird ands. Respond? Oh, no, respond. Okay, sorry I didn't have a special line for that. I just didn't get to that whenever we wrote these. Okay. I'm going to hopefully respond appropriate, maybe a sensory output, maybe eventually having like a motor output, or maybe doing nothing at all. My favorite. Okay, hopefully you can stay within the boundaries here. Central nervous system and peripheral nervous system are the two parts of the nervous system. So we'll put central nervous system over here. Better N. Never do your handwriting on the bus, grade school kids. Oh yeah, that's me. For abbreviation, we'll do CNS, okay? Central nervous system. That consists of the brain and spinal cord only, all right? That's what's considered central. So everything going down your vertebral column in there, and the brain. So everything else, we call it peripheral nervous system. That's easy, right? Or the PNS. So if you see PNS, don't panic. We're talking about peripheral nervous system. And you can assume it's just everything else. There's two types of nerves. And we need to get on them. We got motor nerve and sensory nerve. Could also say neuron. I'm going to talk about later how nerve is actually what we call like a bundle of cells. Okay. Talk about that later. Okie dokie. So the motor neuron is always coming from the central nervous system to somewhere else. Okay. So the info, the signal, we'll talk about how that signal is propagated and transmitted. Info from or leaving the central nervous system. Okay. We call that a motor neuron. Anything that's coming towards the central nervous system, we call that sensory. Okay, you getting comfortable with these little acronyms? That's fun, huh? Okay, sorry, my handwriting kind of sucks, and I'm trying not to get in the border. Okay, so for motor neurons, the response could be voluntary or involuntary. Voluntary is what you're conscious of. Involuntary is happening whether you wanted it to or not, or whether you thought about it. So voluntary's always got to be to skeletal muscles. That's the only type of muscle that's voluntary. Kind of remember that from our muscular system. Involuntary could be to smooth muscle. And this is like an action that we're going to take, or an action your body wants to take. For smooth muscle, or it could be also cardiac, right? Your heart's beating. You're not really aware of it beating. You're not having to make it beat every second. So that's good. Also glands. And other things too, like the iris of your eyes. Those are smooth muscle. Like the little pilomotor muscle in your skin when you get the goosebumps and stuff like that is usually involuntary. Although some people tell me they can make themselves get goosebumps. I go, okay. I'm sure it was somebody in my class just super excited about learning. Okay, we're going to do the functions of the nervous system. Really, we're going to learn, I don't know why. Again, I don't think I edited this first page as much as I wanted to. Had to turn it into a Google Docs. That was painful. Okay, AKA the reflex arc. All right, that's what we're really talking about. And we should just label this reflex arc. Okay, honestly. I don't know what the functions there is. Maybe you want to cross it out. First thing, number one, because this is kind of a process, is sensory input. Got to have something going in. If there's nothing going in and your brain thinks there's something there, that's probably definition of psychosis. Okay? One definition. Sensory input detects changes, okay, in something like changes in temperature, feels sensations. It could be pain, it could be pressure. This is the job of the sensory neurons that bring information to the CNS. Okay? So, yeah. We call that the afferent pathway. If it's coming from the peripheral to the CNS, that might sound a little familiar too, because we talked about it a little bit with homeostasis. All right, so afferent, A comes first in the alphabet. This usually comes first, and it's just gathering information to the central nervous system. The central nervous system will do the integration at some various degree, which interprets the changes to process a response, if anything. You could have a non-response. And then it should organize the information for immediate use and store it for future use, possibly. This all takes place within the central nervous system, CNS. Okay. Then, if we're going to make a response, it's going to arise via the motor output. All right, which is taking the response away from the central nervous system to activate muscles, could be voluntary or involuntary, or glands. This is the job of the motor neurons. And we call that pathway efferent. So you can think of it this way. Afferent, something is affecting you, and then if you're going to do something about it, you're going to, it had an effect, or you're going to, that's the effect of it, of this change that you felt. So also A becomes before E in the alphabet. So there you go. That one's kind of tricky to remember. So yeah, I have this highlighted just to kind of bring it to the front. How well that works. Basic neuron, or AKA nerve cell. Same deal. All right. Yeah, this lovely little guy down here, or maybe it's a lady. I always feel like it's kind of a lady. I'll tell you why. I don't know why. It's got some hairy things. All right, that's what I'm talking about. Like, it looks like to me like this is kind of like maybe Cyclops, and this is her hair. Maybe she's an alien. Actually, this is a cell, right? So that's a cell nucleus on the hairier end. And these hairs aren't really hairs. We call them dendrites. I always remember it as it's like close to the word dandruff, and you get dandruff in your hair. Hopefully you don't get dandruff anywhere else. And so it takes info towards the cell body, okay? So you can think of like an alien antenna, actually, really, with dandruff. And it's taking info in through its antenna, right? Sensing I guess. Doesn't have to be sensing. It's really just taking in a signal. So the signal goes this way. Follow the arrows. We'll talk about what makes a signal and propagates a signal later. Cell body's right here. The smiley face. You know, maybe you don't want to think of the smiley face as the cell body. It really, that was probably a poor choice here. Let's just maybe be like, yay, right there. Oh, that looks weird. That's okay. So the cell body is that whole thing. And cell body actually can get modified and that'll modify sensory information if you want to get fancy through like DNA and what types of proteins are there and whether it's going to enhance the signal or decrease the signal. All right, so the next part of the cell is the axon. I always think of like the axon is what's being acted on. It's going towards the axon. That's the signal right here. Goes down the axon. And maybe this is like the axe handle, okay? If you were, making your nerve into a very small axe. The axon takes the information or signal away from cell body. And each neuron has one, by the way, or more. Okay? So maybe I should distinguish that here. Each neuron has at least one. Okay. Now you notice these little bead-like looking things, kind of exaggeration. What's the bead is really insulation, because in order to transmit a signal, you have to have an interaction between the cell membrane and the outside fluid, and this kind of speeds up the process, so it can just jump and makes it much faster, okay? So you want that. Also, it insulates so that you don't get a signal transmitted to another neuron. Instead, the signal only gets transmitted down that neuron, right? You don't want any literal short circuits, yeah, no short circuits. All right, and it's fatty stuff, kind of like insulation on your wires, so it does not conduct electricity through it or a signal there. Squeeze that in. Fatty insulation. So yes, fat is good. I think I've told you before and preached at you before. Fat is good. You need it in your eyes. You need it around your kidneys. You need it to make molecules. You need it also for myelin insulation so that your neurons work properly. And if you have problems with that, you're going to have like certain types of diseases like MS. All right, so you have to have a good balance of fat. So you don't want to do much animal fats. You want to have omega-3s thrown in there. You want a good ratio of 3, 6, and 9. Okay, I'm done preaching. In between are the nodes of Reinvier. Probably that's the dude that discovered that. So if you discover something, you get to name it after yourself, I guess. So just keep that in mind. So they're just saying that's the spaces in between where the signal actually transmits and interacts with the outside interstitial fluid, I guess. Axon terminals is what, so terminal kind of means end, right? Kind of like the terminal of an airport. Think about when you go to an airport, you're going to catch a whole bunch of different planes at the terminals. These are all axon terminals. So kind of cool. Airport reference. It's also where the signal terminates at the end of the nerve cell. And at these terminals, we suddenly change the signal from electrical really to just chemical. So, yeah. I mean, it's an electrochemical signal. But down here, we're going to talk about the synapse later. These are all the synapses. Synapse. There you go. There's usually a junction here between an axon terminal and another dendrite. Okay, but I guess I'm getting ahead of myself. Okay, so an axon terminal is where you have a whole bunch of neurotransmitter so that you can try to propagate that signal. We'll come back to it soon. Okay, so you got those neurotransmitters. If my hands aren't blocking this too much, and you can freeze frame that and get the rest of the page. All right, so on the back side, actually I don't have a back side. I have one single pages. Yay. I'll try to do this, but my setup, as I told you, is pretty hanky. Peripheral nervous system. We're going to talk about that one first. Why? I don't know. Just decided to pick it. PNS, that's what it stands for. Nerve cells are going to be either somatic or visceral. Okay, so two types. Somatic is to or from skin, skeletal muscle, or joints. I'm going to have like more pencils here. I'm going to go through pencils like crazy. So you're like, what's left? Well, visceral. Remember we talked about how visceral means like the organ itself, like the visceral parietal membranes, stuff like that. They're going to come to or from internal organs, coincidentally. Yeah. Trying to make sure I pronounce that word, parietal, properly, because I learned it wrong. Don't know why. Things stick. Only the dumb things stick with my brain, I'm afraid. Sorry. So that could be smooth muscle. Remember, the intestines are all smooth muscle. Could be cardiac. Could be glands. And that's how you're going to be using the peripheral nervous system. Okay, so a sensory neuron, remember that sensory is going to take in information. So that's where something's affecting you, and you're going to hopefully, measure or sense that thing that's affecting you. So that's the afferent pathway. And the motor neuron is what's going to be the response. And that's what's going to be like the effect of the stimulus or whatever happened. Hopefully. I mean, if you respond at all. Okay. So just blow up here, I guess, for an axon. Maybe that was left over from the other page. I don't know. I don't remember. My axon here is basically wrapped in different types of cells that make the myelin, whether it's peripheral nervous system versus central nervous system. And interestingly enough, we'll talk about those. Schwann cells are for the peripheral nervous system. They make them. And I think of like, things in the periphery need delivery. People aren't close enough to the shopping malls or grocery stores. So the Schwann's truck delivers, I guess, to the periphery. That's what I think of. Okay, so here's the myelin. I know. Hey, if it's dumb and it works, who cares? There's the axon. You can see a little tiny word that says axon there. Okay. There's the Schwann cell. It's wrapped many layers. So the signal is going to just go right through the cell to each node of Ranvier and then interact with this fluid around it. All right, and then here's the axon popping out over here. Okay, I'll write that down. As you can see, there's like bundles of these guys. That's okay. So one type, the sensory of neuron, there's more than one type, but we're gonna kind of like idealize it. You know what I'm saying? We're just gonna be like, okay, here's what they usually all have and stuff like that. We're at the axon terminal here, right? We talked about that terminal part. Doesn't have the cell body there. Why are you starting at the end in it? I don't know. I just like to go backwards sometimes. So, in this case, the cell body, you can see because of the largeness of the size, but also it has a nucleus, okay? So there's a dead giveaway. Darker portion, got the DNA, just like all the other cells, got a full set of DNA in there. All right. So axon terminal is going to take the signal away from the cell body and towards the terminal, where they're going to synapse and hopefully communicate with either another sensory neuron or something from the central nervous system, or usually. Or eventually it's going to communicate with the motor neuron. Okay, so this is for central nervous system. Just reminding you, this part actually is where the peripheral nervous system stops and the central nervous system takes over. So I started you at what's actually in the central nervous system. Good job. Oh well. Just to clarify again, make sure that you know that's the axon, there's the myelin, and the Schwann cell with the little cell body. You see that? Cute. He's got one. Everybody's got one. Produces the myelin, right? Remember that? Produces the myelin. It is the myelin, but it needs fat to do that, okay? Why did I have that down for here when that's supposed to be, I think, actually, no, yeah. I'm thinking, never mind. If it's not in a part of the central nervous system, then it is the Schwann cell. Okay. More on that later, because I have CNS. Maybe I'm thinking it's going to the CNS, but eventually the axon terminal has to terminate somewhere in the spinal column. We'll talk about that. So here's the signal. We got the receptors over here. Okay, so this is closer, your dendrites, okay? We don't call it an axon, even though it might look like an axon. But if it's coming towards the cell body from some other, place of the receptors, then we call those dendrites. Even if you don't have like a whole bunch of them, even though if you have like a single one, excuse me. Okay, so dendrite to cell body from receptors. Okay. So down here, this is the way we're going. We actually call this the neural lemma is just a place for us to label that. Here, we're not talking about the Schwann cell. We're talking about the membrane. Remember sarcolemma for the muscle cell? This is kind of similar. Okay, so nerve cells have neural lemma. That's the cell membrane, which contains growth factors. To repair damaged axons. So that's good. We can't usually regrow nerves after, we are adults, but we can repair. And they're learning how to stimulate growth. So actually, technically, you can, just not very often. So we're saying that in the peripheral nervous system, that's the only place actually that we can really initiate that growth, at least normally. Okay. Receptors, that's what these guys are, by the way. like little Lego man hands. Okay. And the signal goes that way. Receptors could be anything from swirly kind of proprioreceptors, where if it gets crunched, it causes channels to open physically and it'll initiate a signal. It could be proteins in here that are going to sense a temperature change. We don't get too detailed in that, but it's some type of receptor. It could be a receptor for a type of chemical or blood factor. All right. But we're going to carry the info from receptors to CNS. Okay. That was fun going backwards. If you want to try going backwards, go for it. All right, just making sure we know that. For the output, we're going to kind of get how that integrates either in the central nervous system later, but the output's going to be going to the peripheral nervous system via a motor neuron. So we're going to talk about that motor neuron, kind of idealize the motor neuron. It looks more like my first guy earlier with the hair. Lady. I was thinking like curlers or, I don't know, Cyclops alien with a antenna. Okay. So this is the cell body. And we actually have that in the CNS for the motor neuron. It's supposed to be within the spine. I know. We got long axons that go all the way to the peripheral of the fingertips, your fingertips and toes. Okay. Again, nucleus, so if we can identify it, and then here's the dandruff. dendrites. They're kind of like the antenna. They sense a signal from the central nervous system that says, hey, go do the thing. We need a signal saying what to do. Okay, so signal goes in that way. And the signal gets sent along the axon. And it's myelinated. Okay, I'm not sure why it's pointing to a black dot. That's a cell body. We already talked about that from the Schwann's truck, or the Schwann cell that's helping deliver the signal. He's more like a router, I don't know, or a repeater. So let's give it a slogan. Delivering signal to or from PNS for I don't know how many millions of years. There, that's a good slogan. Okay, so it's going to terminate this time, hopefully, in a gland, smooth muscle, skeletal muscle, some type of muscle. So we kind of put some stylized skeletal muscle down here. And here are supposedly the axon terminals. We cut this center section because we're like, okay, it's really long, a lot longer than what we have being able to be represented here. We're talking like feet long. Axon terminals. Okay, that's a neuromuscular junction that we kind of talked about when we talked about the muscular system. Yeah, muscle fibers. So in that case, it's a neuromuscular junction from the central nervous system to muscles or glands. Probably some exceptions. It's okay. You want to label that a muscle cell? Okay. Or muscle fibers, really. Muscle fibers. And depending on how, finely honed your response is, you may have more fibers or less fibers recruited for this. Okay. So, we did good. Let's do the next thing. Central nervous system. Where did you go? Central nervous system. Oh, wow. This is going to be fun. I had to totally get a different picture because I could not scan what I had into Google Docs. So this is, you're going to be like, who cares? But I'm going to be like, okay. It's fine. It's fine. All right. So central nervous system. Just talking about cells in the central nervous system. Neurons highlighted in yellow, okay, or orangey. I don't know. That's kind of. I'll just go stick with yellow. All right. Supporting cells could be all kinds of different colors. Maybe blue, because they're kind of bluish on my page. There probably won't be that blue color for you, so you'll have to put your own supporting cell. Oh, and this is what it's fun, like a group of different supporting cells all coming together to harmonize with your nervous system. So we call it like kind of like Glee Club, but it's glial club for glial cells. Got it? So they really come together. They're diverse, there's, okay. So yeah, you can take that analogy as far as you want. There are many cells in the central nervous system that support and protect delicate neurons. As you can kind of see, I got some dendrites here. And I got some axon with myelinated sheaths. This is the central nervous system. So first thing that kind of stands out is the fact that we no longer have Schwann cells that deliver and help the signal get propagated, I should say, and myelinate and insulate the axons. We have Olga. And Olga's fabulous. Man, you should get an Olga. If you could have an Olga, I mean, she helps the signals to get delivered in the central nervous system. So I kind of think of her as kind of like, not to be insulting to anybody's name, Olga, it's a beautiful name. I kind of think of her as a slightly larger, more stay-at-home type woman that, is very efficient and amazing, maybe. That's my mental picture. Sorry for dragging you into that. So, we like to call them oligodendrocytes. Sure, because, we talked about dendrites, I guess that, yeah, nerve cell lingo. Produces myelin. It is the myelin. It produces the myelin. It's wrapping up the axons. And as you can see, yeah, it helps the signal propagate. So, yeah, there's a lot of people that think they're going to get fat by eating fat. It's not the fat that makes you fat, okay? Let's just attack that misnomer right now. We also like to see that nerves in the peripheral nervous system, they interact with blood capillaries much more easy. In your central nervous system, you don't have a lot of blood. I probably saw that in your cat dissections where, you get cut in the brain and, there's very little blood in the periphery. And in some of these ventricles, which we're going to learn about soon, hopefully. So what happens is you usually have some supporting cells, like ependymal cells, that act as a go-between in the spinal column, at least. So that's kind of down here. How do I want to skip? You want to skip a few? Ependymal cells. Let's just draw. Let's be lazy. Draw a little arrow. That's these. Okay, that's what we're pointing to here. Ependymal cells. And that's just for ones in the spinal column and near the ventricles. But basically, the go between the ependymal cells and the neurons are the astrocytes. And why are they called astrocytes? Because astro, think, space, stars. They look like stars, or asteroids. Here. Remember an asteroid? Isn't that cute? Which means star, but that's okay. All right, so it contributes to the blood-brain barrier. I mean, we're saying it, so if you have toxins in your system, they don't get to go to your brain, all right? Hopefully before your liver and other body parts have a chance to deal with toxins. So it kind of acts as an extra layer and is the go-between. Then, so if you, let's say if you're taking drugs, heavy drugs, they will destroy that blood-brain barrier. That's why it's really important when you go into hospital and you're having procedures done or medication that they know if somebody's been taking drugs or not, because they could hurt somebody really bad because the medication or the procedure is going to go right. There's not good, healthy astrocytes to protect your body from things that are happening in your bloodstream. So yeah, we don't really directly have a blood capillary here because we don't really have them. But we're trying to say here is like cerebral spinal fluid. So I guess that was written down here. All right. Cerebral spinal fluid. Okay, so we're just going to say, yeah, that's what gets you the nutrients and takes away toxins and stuff like that. And then oftentimes, not always, we have the ependymal cells and the astrocyte. We could just have an astrocyte, just saying, that feeds and nourishes the neuron and gives a neuron then in turn what it needs for nutrients and building block molecules and takes away waste. That's it, guys. You have to carry all of the nutrients and waste to and from this system, okay? Another thing that you want to notice is there's these little tiny cells, okay? Hence appropriately named microglia. All right, or glycoglial cell, singular. Yeah, they're in the Glee Club too. They're super proud of it. That's why it's part of their name. The glial club of the central nervous system. And basically, these little guys, you think, oh, they're a little tiny. They probably don't do anything. No. They are awesome. They eat pathogens and damage tissue. So they're not only like cleaning things up, but they also initiate your immune system response. Okay? And we call it cell eating. Remember the word for cell eating? Yes. Phagocytize. Or phagocyze. But we're being fancier. We're going to go be like phagocytizes pathogens. Kids in my class, I know you're damaged goods from having to remember that whole thing. And damaged tissue. And then possibly either getting rid of the pathogen because it got eaten. One way to get rid of your enemies is to eat them. Just kidding. Don't recommend it. But safely digested, maybe with some lysozymes or things in those cells, can also just get rid of a pathogen right there. So we have, if you remember from the immune system at all, from previous maybe classes, that there's other cells that phagocyze pathogens and damaged tissue. These happen to be the specific ones in the nervous system. They're real small, and so they can fit in between, and so that's great. All right, so good for us. We can move on. I kind of mentioned cavities within the brain. I'm not talking about like tooth decay, because cavity just means like cave. But yeah, there are like brain caves called ventricles. It's where your brain breathes. You know, like venting. Yeah. Because your brain doesn't really have its own lungs, right? It has to get its oxygen and all nutrients and through these brain cavities or some capillaries maybe directly. But it's always next to these ventricles. They're full of cerebral spinal fluid, and there is a central canal also down the length of the spinal cord. These open spaces are lined with those kinds of cells we talked about. Ependymal. So it's almost epi with an I, but not quite. Let's make that into a P, shall we? That are ciliated. Oh, they're so silly. Oh, but for a good reason, because that way it can make sure that the cerebral spinal fluid keeps circulating through the central canal and the ventricles, so that you get the more oxygen and kind of get rid of the CO2 that just got spilled into the space, or the oxygen that they're going to need. Hopefully, eventually get some oxygen that you're going to need for the next function here. Okay, so good job with that. That was your central nervous system. Now we're going to talk about synapse. Okay. You're going to be putting more notes on here than this. This, just for funsies. You're like, that isn't really fun. Okay, fine. Synapse. Where and how nerves talk to each other. Okay. So it's a lot like the electrochemical signal at the neuromuscular junction. We talked about with the muscular system. All right. So we're going to do this in like steps. All right. We've got the axon terminal of the up, how do you say, the signal that's the presynaptic cell, so it's before, and then we have the postsynaptic cell here, and that's a receptor for it. So you like the little, so it looks like the claw from the Lego movie. All right, so we're gonna have an electrochemical response. Let's do that first. That's kind of fun. What is this? It's an electrochemical response. It is that electrical impulse, or electric impulse, fine, that travels down the length of one neuron or nerve cell. But neurons use various chemicals then, periodically, neurotransmitters, to talk to each other, and we call that, when it dumps into a chemical signal and back to electric, we call that the synapse. Okay. So to synthesize something, you have two things coming together and making more, so that's why that's synapse kind of language. All right, so number uno, we got to have the electrical chemical impulse. It's already been generated. Okay, electrical impulse down the axon. Always goes down. I wish I had my little electric guitar so I could show you that if you're playing your guitar, which also you could call it an axe, like doo-doo-doo-doo, the rainbow shooting music awesomeness is always going out the frets, and the okay, maybe not. So then this is the, so we wanted to label this. This is the axon terminal. Sorry about that. My hand's going to get in the way. Of your presynaptic neuron. I don't know why I have that in parentheses in my notes. Okay. So, it's going down. We're going to talk a little bit more about that later. But number 2 is going to be that it goes to the terminal, and we have some space up here. It's going to signal these vesicles of neurotransmitter to dump into the synaptic cleft. I always like to say dump because it's real fast. You know, you'd be thinking that would be like, oh, I think I want to go there, and I think I want to do that, and they don't think about it, they just do it. Neurotransmitter is a short distance acting chemical signal, and it gets dumped unceremoniously. Can you see that? Nope, you can't. Sorry. I miss people telling me, Miss Barr, it's me to zoom in, but I can't. You should see my getup. It's hanky. But it works, sort of. So we're happy. We decide to be happy. This, oh gosh, we talked about it being the dendrite of a postsynaptic neuron. It's really the receptor, but it's part of the dendrite. Had to make that longer. Put it in parentheses for some reason. Neuron. Okay. So yeah, the little black dots are supposed to represent the neurotransmitter, right? There's the vesicles. Oh, I'm gonna use a different color. We're kind of next to each other like that. It's, oh, dare I use a pen? Oh, scary. I'm gonna hyphenate. Neural transmitter. Okay. And then the little black dots are supposed to be the neurotransmitter. Okay, let's just do this. What? That thing that we just wrote about up here. That's the black dots. Okay. Maybe that makes sense to you. Maybe you want to color code your notes. Again, that chemical in the synapse makes the membrane of the receptor more permeable to sodium ions, and so it's going to first, let's say number 3. Are we having fun with this pen thing real fast? Let's just, yeah, for fun. Put number 3 here, I guess. Oh, dare I say. First, the neurotransmitter has to bind. Oop, see, told you. Pen. That's why life should be in pencil. Locks onto the receptor. It's a specific protein receptor, so it can only bind to that receptor at that place. All right, and after that, it causes sodium, causes depolarization, and sodium, that's sodium, that's so dumb, rush into the membrane, which then starts, again, the electrical pulse down the neural lemma, all right? Again, so generates an electric current. We call this an action potential, because we got some changes going on and we have a potential for some action. It's like if you have enough depolarization, it's going to propagate the signal in a certain direction intentionally and hopefully cause an action if an action is needed. We can decrease the action potential later if your body decided not to react. Okay, so signal coming this way, going this way, sodium coming in. And then that's gonna travel. It's gonna cause that chain reaction of other sodium when the membrane starts to depolarize. Then it causes other sodium channels to open, and then other sodium comes in and causes that to depolarize. But behind it, you have enzymes, channels really, that are pumping the sodium back out. That's kind of a oversimplified version of that. Okay, so also if you have neurotransmitters sitting in the cleft, you're going to keep depolarizing, you can keep these channels open, and the sodium just can keep leaking in. So it's going to be on all the time. We need to get rid of the neurotransmitter. So what is embedded in the synaptic cleft membrane here is an inactivator. I'm not making these words up. Might be other words for them, but that's one word. And yeah, it is an enzyme kind of locked into the membrane. So maybe put enzyme here. And it's going to deactivate the neurotransmitter, like literally breaks it down. So like, you know, every time you're thinking if it hurts, it's because you're breaking down neurotransmitter that your body is lovingly produced. This is the receptor, by the way. Receptor channel. So yeah, this takes ATP. So this is facilitated or active transport, sorry. Yeah, well, facilitated. And it's diffusion. So it's in higher concentration gradient normally of sodium outside of cells as opposed to inside. And that's what enables us to have the sodium want to rush in because it wants to go down the concentration gradient, you know? So that was fun. Yeah, you'll have to give me questions on that. If you can't remember, my handwriting's kind of messy too. If you can't remember, you might want to review that. Oh, this is supposed to be inactivated neurotransmitter. That's what those little dots are. I forgot. Sorry. Do that in... Oh, I need some better colors. My pencil is getting dull again. And I don't know why, what it is about N's. I have N's in my name, so that's probably why I can't do N's. I don't know, too much in kindergarten, slopping through my work, not doing quality work. Inactivated neurotransmitter. Okay, I'm doing handwriting on the bus. So then your body has to make more, and that's why you're going to need little factors and vitamins and to make neurotransmitters. You know, you need, I think it's lithium, trace amounts of lithium metal to make dopamine. All right, stuff like that. So yeah, your diet is important. Green veggies, good green veggies that are grown and have lots of, I don't know, minerals and stuff like that. And you need vitamins and stuff. Okay, so the nerve. So what is a nerve? Anyways, we just talked about it. It's not just something that you get on when you're at home, you know, with your brothers or sisters or mom or dad. A neuron is a nerve cell, but not a nerve. Okay? In the central nervous system, we're going to have a group of thousands of neurons bundled together in a certain place, I should say. They're usually going the same direction. We call that a nerve tract. So in your brain and parts of your spinal column and stuff, call them nerve tracts. Or white matter. All right? That's because of the myelin. All right? They appear white because of the fatty myelin sheath that covers them, okay? Then if they don't appear white, it's probably because of all the cell bodies, all right? These are going to be either sensory, which are bundles of dendrites, remember receiving the information, or motor, which, remember the acting does the actons, so the axons, at least coming from the CNS, is going to be the axons from the motor. Call them motor bundles, but they're motor nerve cells. And that's what we call a nerve. It's like thousands of neurons grouped together. Because you can see them. You know, if you didn't have a ball bundled together, you would not be able to see the axon or the dendrites of nerve cells. Okay? But Z2 do not mix. You either have sensory coming in or motor going out. Okay, and they do it in certain parts of your spine, which we'll talk about later. Actually, yeah, we're not going to get to your spine till next time. In your peripheral nervous system, a group of thousands of axons and dendrites, now along with blood vessels and connective tissue, because we can actually access blood vessels more directly. It's simply called a nerve. There it is. So you quote unquote only have nerves in your peripheral nervous system. Otherwise, in your central nervous system, we like to call them nerve tracts. Okay. So that's interesting. And they can be either sensory. I hope you have a big screen on your computer as you're viewing this, because I can't zoom in. The sensory nerves are made up of only sensory neurons, like your optic nerve. Okay, so yeah, your optic nerve comes from your eyeballs. That's peripheral to your brain, and it could be sensory. It could be motor, so it could be some output nerves made up of only motor neurons, usually the axons. We talked about that, right? Like your autonomic nerves. Okay, that just means like the ones you're not conscious of. And it could be mixed. Okay, so sometimes we have nerve bundles that are bundles of nerve cells that are both sensory and motor neurons. All right, but it's very specific. Most of your nerves are mixed. Not your optic, but other ones, like spinal nerves, for example. Because yeah, you're gonna have them entering and exiting the areas between the vertebrae and going into the spine in certain specific locations, and you only want to do that so much. So yeah, they come in and out with mixed nerves, and then they get separated out, and they all know where they're going. Okay. So that was the nervous system, peripheral, central, some synapse stuff, and what is a nerve, and some and the supporting cells and stuff like that, and what is all about. A bit of a on the well, I think that's all we're gonna do today, and more later. Okay, you guys are doing great. Forget the reflex arc. That's what I'm trying to remember. That's important to sensory input, integration, and motor output, or afferent integration, and then efferent pathway. All right. So message me if you have questions, and I would, if I were you, fill out the notes if you can get a hold of them, and yeah, review them and color code them and stuff like that, and then we're gonna do some review probably on Quizlet.com and stuff like that. So signing off, you guys have a wonderful day. Thanks for staying with us, and we'll talk to you later. See ya.